me maybe start by thanking the organizers for the invitation. So, as Anna said, I'm a PhD student based here, working under the supervision of Wendy Lowen and Michel van den Bergh. And today I will talk about joint work with them and Francesco Genovese, where we established the deformation theory of T-dg categories. The talk consists of 3 parts, and we start with motivation. Okay. So nowadays, DG categories, and I will define them at some point, arise in various areas in mathematics, for example, in algebraic geometry, in representation theory. And to give a very specific example, they also show up in Kontsevich homological mirror symmetry conjecture. What does this conjecture state? Well, we have 2 mirror categories, and there's an equivalence between them. These are DG categories. And moreover, their deformation theories should also agree. Which brings us to deformation theory. A deformation theory is an old subject, and actually there are many deformation theories, depending on which object you want to deform. And so you can take an object of an algebraic flavor, which I will vaguely call an algebraic object. And then there is the corresponding notion of deformation. And to illustrate this, let me discuss the example of an associative algebra. I think that's the best way to get a feel for this. So we take an associative algebra A over a field K. And then there's a notion of an algebra deformation of A along a ring morphism of commutative rings. It has nice properties. For example, it's surjective. And well, what is an algebra deformation? It is a R algebra, so that if we tensor with K, it will actually just give us A itself again. Let me maybe make this a bit easier by taking a specific map. So if we take K epsilon over epsilon squared, and the map is just putting epsilon to 0, then actually an algebra deformation of A along this map will just be a multiplication on A epsilon, so that if we put epsilon to 0, we retrieve the original multiplication. That's sort of the idea of an algebra deformation. Okay. And then there is a third column. There is a very classic invariant, a very well-known invariant called Hochschild cohomology. And it exists out of abelian groups for any natural number. And this Hochschild cohomology is known to govern the deformation theory. Well, what does this mean? Well, this means for specific values, we actually have a correspondence between this group and either a class of deformations or a notion related to deformation theory. Specifically, we have that the second Hochschild cohomology of A is actually in bijection to these algebra deformations of 2 equivalents for this fixed ring morphism. Okay, I really want you to understand this row, the algebra case. So I want to add some more details to this last claim. So let me at least define this map that gives this correspondence. So to do so, let me tell you what this second Hochschild cohomology group is. Well, it consists of K-linear maps from A tensor A to A, such that some equation vanishes, and well, which equation? forward. You always need to be careful because there are signs. So this should be 0. And actually we're considering equivalence classes, but anyway. And of course this holds for all elements AI in A. And well, we want to get a map to, let me call this class of deformations, the algebra deformations of A along this morphism that I called theta 0. And so what do? Well, we take eta and we map it to the following multiplication. If mu is our original multiplication, and we take mu plus eta epsilon. And I'm not going to do every detail of the proof, but what I want to show now is that this is actually an associative. So to show that it's associative, I need to check, or we need to check two things. We need to compute this expression. And we need to compute this expression. And what is the identity? Yeah? And of course, they should agree. Yes? All right, let's start at the top. Here, I first apply the identity to the first component, and then just the multiplication to the other two, and I will denote it just by multiplying. I do the same for eta epsilon, so I get eta epsilon. Let's apply this mu plus eta epsilon again. So first we multiply, and I'm putting brackets because the associativity is important and not trivial. Okay. We also use the multiplication here. And then we apply this eta epsilon to both parts. Here we get. And then for the fourth term, we have an epsilon squared, but that vanishes because epsilon squared is to 0. So we only have 3 parts.
So what is mu? What is mu?
Sorry? The epsilon to the power of 2 is 0. So this last term is just 0.
Yeah, no, I'm just a bit behind. Like you sent eta to the tensor of A with k, and you put comma mu plus eta epsilon.
That's the multiplication.
Ah, okay.
Yeah. Okay. So here we can just use associativity of the original multiplication. A is an associative algebra. And these two terms are actually the negative terms in this alternating sum. So we can replace these by the positive ones because this equation is 0. And if we do this, then we get, let's not forget about this epsilon. And then actually you can do the same calculations as we did here to indeed retrieve this other expression. So we do have an associative multiplication. And so, okay, let's recap. So we have an associative algebra, we have the notion of deformation, and then the second Hochschild cohomology group actually parametrizes these deformations along this theta 0. You can now just do the whole story for some other algebraic objects, for example, for linear categories. Actually, once you've understood this algebra case, the other ones are just very similar. So you just really generalize this algebra story. the linear category is just a multi-object version of the algebra, so I'm also putting Lin there. And actually, this is due to Geersenhaber, and it was already done in 1964. So then there are abelian categories. And you again have the very natural notion of abelian deformation and abelian Hochschild cohomology. And this is due to Lowen and Van Bergh in 2004. And this list is by no means complete. There are many other algebraic objects we can do this for. And as I mentioned in the beginning, we are interested in DG categories. And there is a very natural notion of dg-deformation and also of Hochschild cohomology. And here I would say due to Kontsevich and Keller, 1994, I would say, or maybe a bit later. All right. And now the question is, well, everything already seems to be there, so why are we looking at this? What is, where is the novelty? Well, actually, this correspondence here that we have in the other cases fails. And this is called the curvature problem. Now, the curvature problem was first studied by Keller and Lowen and Nicolas, and Lowen and Van Bergh. What does it say? Well, it says that, okay, we have DG categories, and these generalize to CA infinity categories. And this is a strict generalization, as CA infinity category is not necessarily DG category. All right. And well, what has been shown is that actually this Hochschild cohomology parametrizes not dg-deformations, but CA infinity deformations. So if we take such an eta in one of these groups, and we do this usual recipe, as I've explained for the algebra, one would hope to find, again, a DG category, but no, in general, we end up with a CA infinity category. So that's the curvature problem. And there is not really one universal solution. You can't really expect this, but there are multiple partial ways of coping with it, depending on the situation you're in. One is done by Keller, Lowen, and is about Morita deformations. Another one is about curve deformation, worked by Lehmann and Lowen, and Alessandro presented this in this seminar not so long ago. And then there are others, and we propose a new one. And ours revolves around these TDG categories in the title that I will also define today at some point.
Can I ask you something?
Yeah.
So the obstructions, like in these examples, they are all vanishing, like one can lift sort of first order deformation to any?
You mean,
or I don't know if
these are just first, these are indeed just infinitesimal ones. If you want to lift it, you need to show to, you need to go to HH3. So abstractions are also measured by Hochschild cohomology, but I didn't really include formal deformations in the table.
But they're all abstracted. This is my question. Or all the abstractions are zero in this example, in these three first examples.
Obstructions to what?
The H3, the HH3 obstructions to go from first order deformation.
No, the HH3 of an arbitrary abelian category does not have to be zero.
Okay.
But the obstructions are measured by HH3. But obstructions is not really, yeah. So okay. These are just really general infinitesimal deformations.
I mean, yeah, of order 1, right? I mean, infinitesimal moving along. But,
right. There's only power 2. So some can be extended, some not, depending on what your HH3 will look like. Yes.
Okay, and this is very well understood in these 3 examples also. It's also a closed theory. One can write down exactly what.
One knows that indeed in these examples, HH3 will indeed have a bijection to the obstructions. That's true. Yeah. So I could put like HH3 and then here the obstructions. That's what I meant by the Hochschild cohomology governs deformation theory. It's more than just the HH2, but I'm focusing on the HH2 because of the example I'm going to give in a minute. Does that sort of answer the question?
Yeah. I mean,
yes or no?
Yeah.
Right. Yeah. All right. So where does this novel approach come from? Where did we get our inspiration? And here is a very important example. So I started this talk by saying, okay, you have DG categories that actually show up in a very natural way in the homological mirror symmetry conjecture, but also in algebraic geometry. And these geometric examples seem to behave a bit better than just an arbitrary DG category. And one very important such geometric example is if we take an abelian category linear over a field K, for example, the category of K vector spaces, abelian meaning you have kernels, co-kernels, and everything works well. Then you can define bounded Derived category, also something I will define in the second part of the talk. And you can take a DG enhancement, and this will be a DG category. So this last row applies to it. And so you would expect the curvature problem to pop up. But actually by a theorem, let me put this theorem here. By a theorem of Lowen-Van and Bergh from their work on abelian deformation theory, we have the following. We have that this Hochschild cohomology of the DG category is actually the same as the Hochschild cohomology of the linear category of, well, you can enlarge your abelian category so that it has enough injective objects. Take the injective objects, these form a linear category. So we're now in this row. And then actually the linear Hochschild cohomology agrees. And this allows us to give a nice interpretation of the second Hochschild cohomology group, not in terms of C infinity deformations, but in terms of abelian deformations of this category A along theta 0. So instead of having these difficult C infinity deformation categories, we now end up with abelian categories. Okay, so there seems to be a different interpretation possible for these Hochschild cohomology groups, not in terms of C infinity deformations. And so this is our inspiration. So our aim for today is to generalize this theorem to similar DG categories. So DG categories like this example, and actually they will be the TDG categories. And also to bigger values of n. So we want this not just for n equals 2, but for n at least 2. And so our first step will be, well, generalize to some subclass of DG categories. What subclass? The class of TDG categories. So the definition of a TDG category is a bit involved. And so the plan for the second part of the talk is to slowly build up towards it, whilst also defining this category that we're using as our leading example at the same time, because this is the most important example. So at least you will have one example to keep in mind. And as before, A will be an abelian category linear over a field K. We start with the definition. CA is the category of cochain complexes in A. What are cochain complexes? Well, they're the sequence of objects in A connected by morphisms in A that together form the differential, so that this differential squares to 0, meaning if we take two consecutive morphisms, their composition is always 0. And we also need morphisms, of course, and we take cochain maps. So given another cochain complex, a cochain map is just a sequence of maps in A from AI to BI, so that all these little squares commute. Yes? Okay, so given such a cochain complex, which I will denote with a bullet, and given an arbitrary integer, you can define the n of the complex as the kernel of the differential in degree n, and Bn of A as the image of the differential in n-1. Now actually, because the differential squares to 0, this is contained in this, it's a sub-object, we can consider the quotient, and this we define as the end cohomology. Right? An example, you can take A to be the category of K vector spaces, and because this is the cochain complexes in vector spaces will be very important, I'm going to abbreviate this category to C of K. All right, important remark. If you take two cochain complexes in A, and actually we can define for all integers K vector space that consists of all sequences of morphisms, now not from AI to BI, but to BI plus M. And this means we're just considering very diagonal arrows. And note also, we're not asking that these squares commute. We're just looking at families of maps. Okay, moreover, we have a map going from this hom A, B, M to hom A, B, M plus 1. So here we have a family of Fi's, where Fi goes from AI to BI plus M. We have the differentials. And here we have Fi plus 1. And we need to map this to a family of maps going from AI to bi plus m plus 1. So in this direction, we can do this by post-composing with this differential, and pre-composing with the other one, and we do both where we put an appropriate sign. Here she is. Yes.
So in the definition of M, the degree M part, you don't ask for commutativity.
No,
Huh?
we don't. This is important, yeah. But I will make a comment about it, and if it's not clear by then, you can. So now we define what I will call the inner Hom. As well, we take all these vector spaces, and we take all these maps together. And actually, maybe you guessed it, this is a cochain complex in vector spaces. So this is really a differential. So we have a cochain complex. We can, in particular, take the Z0 of this cochain complex in vector spaces. And well, Z0 means things of degree 0. So they go from AI to BI. Moreover, Z0 means the kernel, which means the differential vanishes. And that will precisely mean that all these squares have to commute. So now we just obtain a cochain maps. So if you want your squares to commute, Ignacio, then you take the Zn. Okay. So C of A is a category of cochain complexes, and actually all these Hom sets in this category can be endowed with the structure of the cochain complexes in vector spaces. That is what we've just done. And this is precisely.
A in the underlying category is linear over K? Or?
Yeah, A is linear over K.
Oh, sorry.
Yeah, yeah. That's important. So the definition, this is precisely what it means to be a DG category over K. So a DG category over K is a category linear over K, B, that is enriched, and I will explain this in a second, over C of K. What does this entail? This means for all objects in B, you have this inner Hom. That is a cochain complex in vector spaces. And moreover, if you take Z0 of this inner Hom, then you retrieve just the Hom sets in your category. And actually there are some more compatibilities. But yes? Okay, so a DG category is a category, and you have on top of every Hom set this cochain complex, and if you take a Z0, you just get your Hom set. Now you could also take the H0, and if you do that, you get a homotopy category. So the homotopy category has the same objects, but we denote it by H0P, and the Hom sets in the homotopy category will just be the H0 of this inner Hom. Okay. The G category, the underlying category, the homotopy category. That's how you should see it. Example, well, C of A, the category, can be viewed as a DG category via these Homs that we defined right here. And so you could look to its homotopy category. And I'm not sure whether you've come across it, but it's K of A, which is the localization of the category of coaching complexes in homotopy equivalences. Anyway, it's called the homotopy category, but once you know the G categories, it doesn't really say much. So we're not going to use this category, so you don't really need to know it. All you need to know for now is that actually it's not just a category, it's a triangulated category. And for this talk, I won't need the specific machinery of a triangulated category, so all I want to say about it is that it's a category with some structure satisfying some properties. I know that's very vague, but yeah, we don't need the definition for this talk. So this category of coaching complexes we saw is a DG category, and its homotopy category is a triangulated category. And actually this happens quite often in algebraic geometry in these geometric examples that I mentioned. And so we give the baby a name. So a DG category B is pre-triangulated if this homotopy category is triangulated. So as I said, many of these geometric examples are pre-triangulated DG categories. And actually, it moreover usually happens that you're working in the other direction. So very often you're actually starting out from a triangulated category, and then you ask, is there a DG category lying above it whose homotopy category is this triangulated category? Why? Well, these objects are a bit difficult, and DG categories behave a bit better. So we usually want to work with this thing and not this thing. And if such a DG category exists, then we call it an enhancement. So we call B a DG enhancement of H0 of B. Yeah.
Is this definition of pre-triangulated equivalent to the one of the Oneida?
Yeah.
Oh, okay.
Oh, yeah.
Okay.
There is actually always a triangulated structure if you apply the Oneida, and then you just ask that you can pull it back to B itself.
Okay.
But then actually there is a distinction to be made between pre-triangulated and strongly pre-triangulated.
Okay.
And
but I think. Yeah.
But philosophically it's the same. Yeah.
Okay.
But
so this is strongly triangulated.
Sorry?
So this condition is strongly pre-triangulated.
No, if we mean strongly, then I will. Strongly means, so you know the definition with the Oneida?
Yeah.
Well, you have Z0 Oneida and H0 Oneida, full banks.
Okay.
And if you want Z0, that's stronger, so that's strongly.
Okay.
But actually, strongly pre-triangulated will show up at some point.
Okay.
But up to quasi-equivalent, it doesn't matter. All right. Yeah. So, okay, I've given you so many definitions. So let me maybe turn back to our example. Okay. All right, so example, well, we've already seen, already said that this is actually a pre-triangulated DG category. And then there is a second example, which is the one that we were aiming for in the first place, and that will be this one. And to define it, I will first define a subcategory of this first example. So I first define A, C, D, G, A as the subcategory, DG subcategory on the acyclic complexes. So as our objects, we only take the acyclic complexes. And what does acyclic mean? This means that the complex doesn't have any cohomology. So if all these cohomology groups vanish, then it's acyclic. And now philosophically, when you're doing homological algebra, as soon as something doesn't have any cohomology, you really want to perceive it as zero. Really the object zero on the nose. Not something whose cohomology vanishes. So actually, instead of working in this category, we want to work in the quotients by the acyclics. Because there, an acyclic complex really is zero. And this thing will be dg of A. And if you then take the homotopy categories, because these are dg categories, then you get d of A which you may know as the derived category of A. And well, this quotient preserves the pre-triangulatedness, so this is pre-triangulated dg category. Now the attentive listener will have seen, okay, this is actually not the object we want. We're missing one thing, and that's this superscript b. Well, if you now consider when we have a quotient complex, you can ask that's outside of certain degrees, it will only be zero. Such a complex is, of course, called bounded. The important parts, certainly in this category where we quotient things with zero cohomology out, here we really assume it to be zero. Well, if we just only consider bounded complexes everywhere, then we get this dB/dg of A. And this is the example that I started this talk with. Okay, so you would maybe now think, okay, we have found a class of dg categories that are similar to this dB/dg of A, namely the pre-triangulated dg categories. So aren't we there? Well, actually, there's one more property of this category that we will meet. So one last definition. Okay. And that's the definition of a T-structure. So a T-structure on a triangulated category, so on the homotopy category, T is a pair of subcategories satisfying three conditions, and we won't need them. So just think of it as a nice pair. And given such a nice pair, you can define some other things. For example, the heart of this triangulated category with the T-structure, which is just going to be the intersection. So this we call the heart. And then the heart is, of course, a subcategory. Yeah? If you intersect subcategories, it's still a subcategory. But it's actually an abelian subcategory of T. And there is also a functor going from the triangulated category to the heart, and we call it, for a very good reason, the zeroth cohomology. And this reason will show up in a second. So, okay, we now have a lot of levels. We have the DG category, we have the underlying category, we have the homotopy category. This is triangulated, comes with a T structure, and inside it we have the heart, which is abelian. Okay, so you should really think of them as on top of each other. The more you go up, the more you sort of have. Okay, and this is not enough space, so let's create space. But this I will leave. So let me make it here. Example. We already know that dg of A is pre-triangulated, and I claim that it's moreover something I forgot. A TDG category. Okay. The TDG category is a pre-triangulated DG category be such as this homotopy category has a T structure and so I claim this is a TDG category. So the only thing we still need to do is to come up with a T structure. Actually, triangulated categories can have multiple ones, but for this one, there's a super nice one, which we call the standard T structure. And it's defined like this. So in our smaller than zero parts, we take the complexes that don't have any cohomology above zero. And of course, in the bigger than zero parts, we ask that they don't have any cohomology below zero. And so this is a T structure. You can then look to the heart of this T structure. And actually, this will just be the abelian category itself. And there is this functor, the zero cohomology. Actually just maps a cochain complex to its zeroth cohomology. And so this example of dg of A has even influenced the terminology we're using, so it's really important. Okay, so now you know what a TDG category is, or at least you have one example in mind, and then we can get on with the story and go to our aim, which was to deform these TDG categories.
So this is the same as asking that from n bigger than 0 is 0, right? Because you're quotienting out by a cyclic stuff, or not?
Yeah. Okay. Yeah. But it's
when you declare like a cyclic complex to be treated.
Yes, that's true. But you should sort of.
Maybe
you should then give a no. Philosophically, yes, but you should then give an argument of how you can sort of split up a complex where some part is acyclic but not a full complex, and then there you need the triangulated structure to write this complex as this acyclic one and the non-acyclic one, and this will indeed be 0 in the quotient category. So you need to sort of give a way of splitting up the acyclic part from the rest. But as soon as you've done that, then actually, yes, you can, in this category, just assume that this complex really only has zeros above n, above 0. Right? That's the question, huh? Whether you can really think of...
They are complex if there are 0 from 1 on. Yeah.
Yes. Mm-hmm.
And so, is it true that in general, in this category, you can just identify each object with each column with the chain of cohomology?
No, that's only true if you have the extra property of being von Neumann, I think. Or there's at least a name for these categories, or maybe it's not.
Semi-free, maybe?
Yeah.
What is the problem?
Semi-free?
Semi-split.
Semi-split?
Something like that.
Yeah.
Dimension to be 0.
Sorry?
The cohomological dimension to be 0.
Yes, but there's a name for these. I think it should be 1, or is it 0? Yeah, it's very low at least. But there's a chapter in Bible, and they are given a name, which mostly means that no, it's not in general the case. But there are some examples. Yeah.
Wait,
So,
what
thank
was the
you.
question? Sorry. If you can identify.
A complex with its the cohomology of the complex. Yeah.
Okay.
So no, actually there are some subtleties because quasi-isomorphisms become isomorphisms, but not all isomorphisms come from quasi-isomorphisms. Not all quasi-isomorphisms come from Cauchy maps. Blah blah blah. So, but yeah, there are some nice settings. But indeed, as she said, you should look to low cohomological dimension in Bible, and then you will find them. All right, so we now know what a TDG category is. This is our aim, or rather to generalize this theorem, that's our aim. And so actually what we want to do is, okay, so let B be a TDG category. And for simplicity, let's call this homotopy category T, not much shorter anyway. So what we want to do is we want to put B here on the left-hand side. And then the question would be, all right, but these things, we need TDG analogons for these things. Because they're very well defined for dB of A, but they're not so defined for an arbitrary B. And so as soon as we found these analogons, then we're able to state the theorem, which will in the end be our theorem. And that's the last part. And let's start with this first question mark. Again, a definition. Derived injective in T. T was our homotopy category, so it's triangulated. Is an object Li such that if we take the morphisms into this object, then actually this will be the same as applying our zeroth cohomology. So we're going to the heart, which is an abelian category, and taking the humps in this heart to an injective object I. So how to think of a derived injective object? We have an object in our triangulated category. We take morphisms into it. Well, this is the same as first going to the heart by the theorem of cohomology and taking the morphisms into it there. And there it's an injective object, which is really nice. Injective objects are just nice. Okay. Then you can define dg injectives of B as the dg subcategory of B on the derived injectives. An example.
A question? Do you need to fix the height?
Sorry?
Do you need to fix the T structure?
Yes, the T structure is indeed fixed. So we're starting from a TDG category, and in the definition of a TDG category, we fixed a T structure.
Okay.
But usually I would put let B be a TDG category with T structure, blah, blah, blah. Yeah, you're very right. You should fix the triangulated structure and the T structure. Yeah.
Is there really a functor L? No.
It's a quasi-functor.
Okay.
Okay. The derived injectives, this category, are, you will have seen this coming, just the injectives. And this is great because we want to just have the injectives. Because we want this theorem to be just an instance of the general theorem we're building. Okay? Yeah.
What do you mean exactly? So the injectives of A are objects in the abelian category A.
Yeah.
Well,
And that's the heart of this T
so
structure.
the derived injectives are objects in the heart.
No, the derived injectives are objects in T. Their cohomology are objects in the heart. But in this special case, the derived injective won't have any higher cohomology.
Okay, so the derived in that case, the derived injectives will be objects.
Exactly, but this is very rare. Usually they have a lot of positive cohomology. But what you say is maybe actually related to what I wanted to say next. This is a DG category, so subcategory of DG category, but actually it will be cohomologically living in non-positive degrees. Why? Because, well, here we have that they're concentrated in just 0 degree, and actually we can only have positive degrees, so morphisms between them will only live in negative degrees. Very vaguely put. But this will mean, and I'm being very short here, I know, this will mean that actually in this curvature problem that I started this talk with, well, this won't show up if we're considering DG categories that are cohomologically concentrated in non-positive degrees. So this is a good sign. This means we're really dealing with this problem. All right. Then we need the second last ingredient, I will say. So let me maybe first say a bit more about this int of A. So in the abelian, it's a construction in abelian category theory. And why? Well, A may not have enough injectives. For example, if A is the category of coherent sheaves over a scheme, it will not have enough injectives. And injectives are nice, so you want them to have enough injectives because then if a category does, then these are sort of the building blocks. And so luckily there is this construction where we can go to a bigger category, embed it in there, and this will have enough injectives. And if A does not have enough injectives, then actually this dB of A also won't have enough derived injectives. And so similarly, we really want to embed this into a bigger TDG category that now has enough DG injectives. Theorem. So I will now state this theorem I will give the proper statement, which means there will be some conditions that I haven't explained, but you can really ignore them because they're not really, they're just really technical details. They're not giving any extra interpretation to that. So B will be a TDG category, but it will also be essentially small and strongly pre-triangulated. Environment, but that's something we actually already have. Then, first, there actually exists such a TDG embedding. So this is the TDG category, which means it has a homotopy category. And this homotopy category is triangulated, so it has keys at the F. If the TDG category it has a heart. And if we compute this heart, then actually we're just going to recover this abelian construction, which is already a good sign, because we want to retrieve this in. And then secondly, and this is what we want, this bigger TDG category has enough derived injectives. And then an example. So as I mentioned, very often this doesn't have enough derived injectives. So we will want to apply this construction. This will give us a bigger derived category. And if you then take the derived injectives, well, we've seen that these are just the injectives of this abelian category. And this is precisely what we're looking at. So, okay, so we really have our missing pieces now, which means I can, maybe I will put it in a color, finally states our theorem. And actually here we need again these conditions that we had in the statements. So first we have the cohomology. B is just that of the derived injectives of this int. And secondly, for all n at least 2, it's okay. We have the HHN dg-E is now the bounded T dg-deformations along theta 2 minus n. So this was question 1. With, well, theta 2 minus n will again be going from this k epsilon to epsilon squared to k. And we're now giving epsilon a degree. And the degree will be 2 minus n, and n is at least 2, so this will be a negative degree. And if n equals 0, then actually, sorry, n equals 2, then actually it doesn't have a degree at all, and it's just this theta 0 that we saw in the very beginning with algebra deformations, which makes sense because we only have the case 2 here. And in the abelian setup, we can't have negative degrees. And the reason why we're able to obtain this more general result is, again, because this thing actually only has a non-positive cohomology, so there is no curvature. for this DG category. Okay, and so to recap, so we have found actually a class of similar DG categories, namely the TDG categories, for which we can capture this phenomenon and generalize to larger values of n. And that's all I wanted to say today. Thank you.